Hi, and welcome back to the NeuroBytes video experiment series. In a previous video, you learned how NeuroBytes touch sensor neurons send signals to interneurons and how the interneurons process that incoming information. Now we will learn about another sensory neuron simulator, the NeuroBytes Rod Photoreceptor. Rod photoreceptors are unique in several ways. Even though they are sensory neurons, photoreceptors are found in the retina, which is considered part of the central nervous system. Unlike cone photoreceptors, which detect red, green, or blue light best, rods are best at detecting changes in overall light and dark, particularly at lower light levels. Real rod photoreceptors in your eye are also unique in that they are maximally active when there is no stimulus, or light, hitting them. In the dark, they release neurotransmitters onto neurons called bipolar cells. When light photons hit rods, they reduce the release of neurotransmitters. Rod neurotransmitters are mainly inhibitory, meaning that they hyperpolarize bipolar cells. So, when light hits the rods, they reduce their inhibition of bipolar cells, and these cells then can excite ganglion cells, which send the visual signal into the brain itself. A third way that rods are unique is that they, as well as bipolar cells, don't fire action potentials. They are so short that even the resting voltage level can stimulate the end of the cell to release neurotransmitters. This end of the cell is called the synaptic body, not the axon terminal, since they don't have real axons. So, your NeuroBytes Rod Photoreceptor is a bit different than the other neuron simulators you've seen so far. At one end of the rod simulator, called the outer segment, there is a light sensor, which detects the light in your environment. On the underside at the other end, called the synaptic body, there are two separate outputs instead of one, dark and light. The dark output is similar to output of real rods in that it's maximally active in the dark. To make the rod simulator even more useful for experimentation, there is also a light output, which is maximally active in the light. Since rods don't fire action potentials, the LED indicator system is different on your photoreceptors. The small LEDs on top of the rod simulator above the light and dark connectors are dim with low connector output and glow brighter with increasing connector output. The real rod photoreceptors in your eye are very good at adjusting to different light levels as you go about your day. For example, when you first walk into a dark theater, it's hard to see anything, but then eventually you get used to the low light levels. In the bright light, photopigments in the rods are used up or bleached, and they take some time to regenerate when you move into a darker environment. When they do, it's easier to see because you've adapted to the dark. Your rod simulators also have a way to adapt to different lighting settings. Let's try that now. Power up one of your rod simulators with your battery pack and power cable. When you see the power button icon on the screen, this tells you that your simulator should be powered up. It should be located in a part of your room with normal lighting. To set the minimum amount of light that your rod will respond to, hold your hand an inch or two above the light sensor to block most of the room light and press the 0 button. To set the maximum amount of light that your rod will respond to, move your hand away, exposing the sensor to full light, and press the span button. After this adjustment for your ambient light, the light LED should be at full brightness if the sensor is not being blocked, and the dark LED is off. Move your hand over the sensor to create a shadow and watch how those LED patterns change. You should notice the light LED dimming and the dark LED growing brighter. These LED patterns are telling you about the output from the rod to a postsynaptic neuron, so let's connect one up now. Plug in an excitatory neurotransmitter cable into your dark output and then connect it to one of the long dendrites on the interneuron. Be sure that your light sensor is in full room light. What do you predict will happen to your photoreceptor and interneuron as you begin to cover the light sensor up with your hand? Now, disconnect the excitatory neurotransmitter cable from the dark output and move it to the light output. What do you predict will happen to the photoreceptor and interneuron when you begin to shade the light sensor now? Since real rod photoreceptors release inhibitory neurotransmitters, now would be a good time to experiment with your inhibitory neurotransmitter cables. You're going to run the same experiments you just performed with excitatory neurotransmitter cables, but before you do, how do you predict the interneuron will respond to the inhibition from the dark and light outputs? After you've made your predictions, take a blue cable out and try the same experiments you just ran with the excitatory neurotransmitter cables. Did the results match your original hypotheses? If not, how and why were they different? What you should have seen is that for each dark or light output, the excitatory and inhibitory neurotransmitter cables produce opposite results. When the rod is in full room light, excitatory cables on the light output will depolarize the interneuron, while inhibitory cables will hyperpolarize it. When using the dark output with a shaded or completely blocked sensor, it's the same. The excitatory cables depolarize the interneuron, while inhibitory cables hyperpolarize the interneuron. And when using a dark output in the light, or a light output in the dark, there should be minimal or no change of the interneuron, regardless of the type of neurotransmitter cable connected, since the outputs are not active under their non-stimulated condition. In this video, you've learned how to add light sensing to the touch sensing neural circuits you've experimented with previously. Have you built something fun and interesting that you want to share with the world? Visit us at neurotinker.com and show us your brain power.